So we want models to be able to account for these trends so that we are able to get more consistent and more accurate estimates of demand. Can we do so? Yes. And this is where I introduce to you method 6. This is called the trend adjusted double exponential smoothing. As we'll see later, this is motivated by the fact that we have two exponential smoothing models in the forecast. So in general, to forecast demand, you have the forecast of average demand level plus the forecast of trend. So in the last 5 models, what we have is the left hand side, but not the right hand side. In this model, we include the right hand side so that we can also incorporate the trend estimates in the forecasting model. So this is how it looks like in terms of the equation, but I'm going to show you the more formal equation at the bottom of this slide. Okay, so let's break down these equations. So we have forecast for level. This is the demand level, right? So smooth demand forecast, as you can see up here. We have alpha that you need to decide. A sub t is the realized demand, and then S sub t minus 1 is the forecast for level in the previous period, and T sub t minus 1 is the forecast for trend in the previous period. Then we do the same for forecasting for trend, so T sub t, and we need to determine what beta is here, and we have beta S sub t minus S sub t minus 1. So these are the forecasts for level in the current period and in the previous period. And then we incorporate 1 minus beta times T sub t minus 1. This is the forecast for trend in the previous period. And so based on this top equation here, the forecast for next period will be equal to sub t on the bottom here, S sub t plus T sub t. Okay, so as you can see, these two equations resembles the exponential smoothing, and because there are two exponential smoothing, so we can call this the double exponential smoothing model. So let's take this to an example. So assume that S1 and T1 are already chosen in some manner, and further assume that alpha equal to 0.3 and beta equal to 0.4. Okay, so with that, we can start to do the forecast for period 2 based on S sub t plus T sub t, and this will be S1 plus T1, right? So we have 100 plus 1, I get 101. Moving on, now that I realized the demand for period 2, that's 105, I can then calculate the S where t equal to 2, and that would be based on this equation, 0.3 times 105 plus 1 minus 0.3 times 101. And I get 102.20. Alright, so just to be sure, this 101 comes from S T in the previous period and TT in the previous period, right? Next, I can calculate T2. So that will be 0.4 times 102.2 minus 100. Okay, 102.2 minus 100. That's ST in the previous period. Plus 1 minus 0.4 times 1. This 1 comes from here, and I get 1.48. With that, I can then sum this value and this value to get my forecast for the next period, which is period 3. With that, I get 103.68. Do the same for the rest of the cells, and we can advance the forecast to period 4, and then to period 5, and then to period 6, and lastly period 7. Here, I will encourage you to pause this video at this point and work through each of these lines carefully. The full equations are given at the top of each cell, so you can follow that as you work out the values. Next, I would like to introduce to you the last method, method 7 on linear regression forecast. This is extremely powerful yet simple, as you might already know, so I just want to step through this very quickly. The assumption here is that we have a variable that we want to forecast. We can call this as a dependent variable, and this is related to other variables in the environment, so we can reflect this down in the equation. Many also call these variables the independent variables or explanatory variables. They all mean the same. So in this course, we will consider linear models with a single dependent variable and a single independent variable. So that's reflected by y, the dependent variable, and x, the independent variable. Alpha here is the intercept, and beta here is the slope. The full equation for the estimate of alpha, that's alpha hat, and the estimate for beta, beta hat, are given by this. For this course, you do not need to know exactly how to derive these parameters, so you don't have to memorize them at all. In Excel, you can simply use the function intercept and slope to obtain the estimate for alpha and beta respectively. So essentially what we have here is a linear regression that draws a straight line through the observation points that are realized in the data, right? So if we have advertising on the x-axis and sales on the y-axis, the red line is what would come from the linear regression equation after you have estimated alpha and beta. So let's take this to an example here. What is the forecast for sales in the 21st day? Given that you know the forecast for sales from day 1 up until day 20. So we can use Excel to derive or to estimate the alpha and beta, and this is the estimated value. And so the forecast for 21, which is day 21, alpha will be the intercept, that's 100.64, and then beta, the slope, is 1.9293, fit in here, multiply by 21, work through this, you get 141.1553. Okay. So with that, I have concluded the 7 forecasting models, and I want to cover on how to measure forecast error in the next segment of this lecture. So I'm going to introduce to you 3 different methods here. And to do so, let's define some notations. So all measures start with per period forecast error. So we have forecast error here, sub t. So this is represented by E sub t. And this is equal to the actual demand or the realized demand of the current period minus the forecast of the current period. So that will be A sub t minus F sub t. And the difference will give you the error, right? Or the absolute deviation from the realized demand given a forecast. So in the next 3 slides, we will go through 3 different forecast error measurement techniques. And in general, we want a forecasting model that generates the smallest error. So this is the first technique, MAE, mean absolute error, also referred to as the mean absolute deviation, MAD. And the equation is as such. You calculate the error for each period, take the modulus, so it doesn't matter if you have negative sign, you just want the absolute value. You sum it over t periods and divide it by the number of t periods. Alright, so let's take a look at one example here. So from period 2, you take 155 minus 130, you get 25. So the absolute error is 25. In period 3, I have 145 for demand and 155 for forecast. Subtract these 2 values, you get minus 10. So because I'm getting the absolute error, I will remove the minus sign and only take the positive 10. You do the same for all periods, and then you can divide by 5. We have 5 observations here, and that's t. and that will give you the MAD or MAE of 13.40. Right? So in general, we want this value to be as small as possible. And whether this is good or not, you need to compare this with other models using similar measure for your error computation.